Okay, so what we're going to try to do in this video is make a mapping between the collars and the dogs from the planet Zog. So we'll make a list of all the collar numbers here. 0, 1, 2. So these are all the collars that I've taken in my spaceship to the planet Zog. And this is the name of the dog that gets that particular collar. Now what I'm going to be trying to do is to map from the natural numbers to the real numbers, but only in the range 0.0 up to 1.0, up to 1.0. So I'm only in that range there. Okay, well let's see if we can do it. Okay, so in the range 0 up to 1, I've got the first dog, and it's going to be 0 point something, or it might be 1 point something, but I'll do a 0 point something. And then it's going to be a string of digits after here. So I'm just going to take some random digits, 3, 1, 6, 9, 1, 7, 4, 3, 2, 6, and then it's dot, 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 dot. Basically it runs on. This is just the first Zog dog that ran into the pen, as it were. And I gave that dog collar number 0. Okay, so that's cool. Let's give collar number 1 to the second Zog dog. So it's not going to be this one. We won't get that one again. It'll be a different one. So let's do a different number. Let's do 3, 1, 6, 7, 1, 7, 7. Now what you notice here, this number is very, very similar to the first one. Very similar indeed. I've just chosen a very similar number. But you'll notice that one of the digits is different. And that tells me it's a different number. If any of the digits are different, it's a different number. Okay, third Zog dog that runs up is going to get collar 2. Well, let's just do 1, 2, 3, 1, 2, 3. It doesn't really matter what I'll put a 6 on the end just for fun. The idea is that the dogs are running in any old order. 7, 8, 9, 2, 6, 1, 3, 5, 7, 2. Any of these might be the telephone number of someone interesting and important. I've no idea. So let's do 6, 6, 6, 6, 6, 6, 6, 6, 6, 6. That's 0.6 recurring. Let's have a small number here. 0.00000000002, and then so on and so forth. And the idea is that I continue doing this, and all of the Zog dogs that have got names between 0 up to 1, they each get a collar. And my hope is that I've got a collar for each and every dog. So dog 6 is going to get a collar, dog 7 is going to get a collar, and because there's an infinite number of these and an infinite number of collars, you might think, okay, that's fine, you just run on to infinity. The problem is this. There was a mathematician called Cantor. This one wasn't due to Euclid, this one was due to a guy called Cantor. And Cantor was particularly interested in infinities. And what he wanted to show was that the number of real numbers on this side is actually more than the number of integers on this side. And the way that he did this was to show that no matter what arrangement you choose on this side, no matter what order you put these numbers from 0 up to 1 in here, there's always going to be a dog on this side, a number on this side, in other words, for which there is no collar. And the way that he did it was this. It's called the diagonalisation argument. So I'll write that here. Diagonalisation. Okay, so the diagonalisation argument works like this. Let's take the diagonal of this table of numbers. So that number 3, and then the 1 there, the 3 there, 2 there, the 6 there, and the 0 there. Okay, and so on and so on. So, you know, basically going on all the way down the diagonal here, all the way to infinity. Let's now make a new number. So this is the clever bit of the argument. Let's make a new number whereby if I have a 3 there, in my new number I'm going to write 4. And if I have a 1 here, in my new number I'm going to write 2. In other words, I'm going to add 1 to each of the digits. So this new number, we'll call it new dog, or maybe unlucky dog as it turns out. New dog is equal to 0. Well, it's a 3 there, so I write 4. It's a 1 there, so I write 2. 3 there, so I write 4. 2 there, so I write 3. 6, so I write 7. A 0 there, I write 1. You may be wondering what I would do if I got to a 9. Well, I'd write 0, basically. It doesn't really matter, actually, as long as I write a digit other than that one. Now, the question is, has this new dog got a collar? Well, what we know is that new dog, whose name I've written here, hasn't got collar 0. I can guarantee that because this number and this number are different. They're guaranteed to be different because of the procedure that I did. So what I said to you here was that because that number and that number are different, those two dogs are different. So this dog and this dog are a different dog, and that dog has already got collar 0. So new dog does not get collar 0. Sad. Right. What about this one? Okay, let's look at this. Does new dog get collar 1? Well, no, because collar 1 has already been taken by this dog, and we definitely know that this dog and this dog are different because they have a different number there. So new dog doesn't get collar 0 and doesn't get collar 1. What about collar 2? No good, because the digit here and the digit here are different. So collar 2 is taken, collar 3 is taken, collar 4 is taken, collar 5 is taken, collar 6 is taken. The diagonalisation argument shows us that all the collars are taken, and yet I've made a dog which has got no collar. So there's no collar for this poor old dog. And in fact, you can make a huge number of dog names which have no collar just by, say, adding 2 to the digit rather than 1, or just all you've got to do really is just choose a different digit. So I could have another new dog. So let's have another new dog and another one. Then I could take okay, maybe I'll subtract 1 this time. So 0.2, 0, 2, 1, 5. Well, there's a 0 here, so I'll turn that into a 9. Similarly, no collar for that dog either. So there's a lot of dogs who've not got a collar. And what that shows you is that this interval here is a larger infinite set. So this is a larger infinite set than n0. We call n0 a countable infinite set. It's not a very good name. but it basically means that you can start listing the elements. Listable would be better. Whereas the larger infinite set here, R between 0 and 1, is called an uncountable set. Uncountable. And we're going to be hearing more of that term later.